Hello, hi everyone. So in today's video, we are going to go over this paper, GSM-Infinite. How do your LLMs behave over infinitely increasing context length and reasoning complexity? This is a preprint from earlier this year. I'm not sure if this has already been accepted somewhere. I don't think it has just yet. Yeah, but it's probably under review somewhere. And the authors are Yang Zhou, Hong Yin Liu, Zhou Ming Yuan Dongshan, and Wei Shen from CMU and Meta. I'm really sorry for mispronouncing those names. All right. So this seems very interesting. This is also related for a short dev stint that I'm doing, and I just wanted to read the paper to get a better idea of what they've done. And also, I thought might as well record. All right. So long context large language models have recently shown strong performance in information retrieval and long document question answering, right? However, to tackle the most challenging intellectual problems, LLMs must reason effectively in long and complex contexts, like frontier mathematical research, where studying how LLMs handle increasing reasoning complexity and context length is essential, yet existing benchmarks lack solid basis for quantitative evaluation. Inspired by the abstraction of GSM 8K problems as computational graphs, and the ability to reduce noise by adding unnecessary nodes and edges. We develop a grade school math problem generator capable of producing arithmetic problems with infinite difficulty and context length under fine grained control. I believe this is uh, what one of the physics of LLM papers did to generate synthetic data. Using a newly synthesized GSM-Infinite benchmark, we comprehensively evaluate existing LLMs. We find a consistent sigmoid decline in reasoning performance as complexity increases, along with a systematic inference scaling trend. The exponentially increasing inference computation yields only linear performance gains. Ah, interesting. These findings underscore the fundamental limitations of current long context LLMs and the key challenge in scaling reasoning capabilities. Our GSM Infinite benchmark provides a scalable and controllable testbed for systematically studying and advancing LLM reasoning in long and complex contexts. Yeah, sounds super interesting. Mm, alright. So, introduction to recent state-of-the-art long context LLMs. What is team at all? Oh, Gemini team. Yeah, maybe you should fix the representation in your study. Anyway, have achieved astonishing performance in tremendously long context. Uh, Gemini achieves near perfect performance in 10 million multimodal retrieval and long document QA. However, for long context LLMs to contribute to cutting edge mathematical and scientific discoveries or function as autonomous agents, they must be capable of processing dense, complex information and reason through multi step tasks. For example, Sir Andrew Wild's proof from its last theorem in 1995 spans more than 88,000 highly compact tokens with deep logical connections, making context level RAG insufficient and highlighting the need for long context LLMs. Therefore, it is crucial to benchmark and facilitate long context LLMs for complex reasoning and high density information processing. I'm not quite sure how do I feel about this example. I see the point that they're trying to make, but this is like one of the biggest mathematical problems, uh, at least of that. Even today, I don't think many people understand the proofs that intervals came up with for formats last forum. And there's certainly stuff which lies between grade school math and for the proof of formats last theorem, which uh, requires a lot less context heavy element. But yeah, I see the extreme case that they're trying to make here. Although widely used, current long context benchmarks do not fully measure the true potential of long context LLMs, making it challenging to measure the progress towards advanced intellectual agents. It is mainly due to three reasons. Okay, low complexity. Many long context benchmarks, such as long bench, and most tasks in ruler focus on retrieval or summarization, which involve low reasoning complexity. Similar to this, we found that simple context level RAG achieves on par or even better results than long context LLMs shown in figure 3. Okay, this is interesting. Detectable noise. Many tasks are innately short context but are bloated into longer context through semantically irrelevant filler text, and variable tracing, which is easily distinguished by a retriever of local context level RAG. And then row resource. While complex long context tasks exist, such as long code completion, they lack sufficient high quality examples with adequate and verified annotation for labeling. Okay, makes sense. I'll just go over the figures as well once. So this is the performance at 16K context length. This is models in bubbles for performance versus price. Okay, valuation of 10 powerful LLMs on this test, comparing API generation cost, which is the horizontal axis. Okay, so 10 USD per minute token. Okay, zero context reasoning ability, vertical axis. Bubble size represents reasoning performance at 16K context length. So Gemini has uh, so maybe uh, it's zero context reasoning ability is something they will describe later. And they haven't yet referred to these figures, so maybe I'll wait for a bit. But they referred to figure 3, so I need to check there. You can see that LLM, one pass RAG, and interactive RAG. So LLM and interactive RAG are virtual. In fact, in some cases, it also beats it. Interesting. So ideally, a long context reasoning benchmark should offer controllable and scalable complexity, incorporate hard to distinguish noise, and support infinite data generation for continuous and adaptable eval. Makes sense. So, inspired by these two papers, they model reasoning problems as computational graphs attached with language semantics. By adjusting their structure and complexity, they gain fine-grained control over the reasoning difficulty and enable infinite scaling. So, instead of inserting semantically irrelevant filler text, noise is introduced as additional nodes and edges upon the core graph, strategically connecting to existing nodes without affecting the necessary reasoning steps for solving the task. This design enables the generation of arbitrarily long test examples from which context-level RAG finds it hard to differentiate relevant information from noise. Makes- yeah, this sounds all of this sounds good so far. However, several technical challenges must be addressed to construct a practical benchmark. First, we need to ensure diverse reasoning patterns and operations, ideally providing a comprehensive coverage of GSM 8K to have fair evaluations. Second, the computational graph must be effectively translated into natural language that is both human and LLM readable. So it should eliminate ambiguity from memorization and ensures a clear focus on reasoning. And so they introduce GSM-Infinite, a long context benchmark that scales and controls reasoning complexity and noise through fine-grained manipulation of computational graphs, enabling their translation into diverse human and LLM readable problems. So in 3.1, 3.2, we discuss how to control and scale reasoning complexity, and in certain noise 4.1 discusses methods to ensure comprehensive coverage of reasoning patterns, and 4.2 shows ways enabling the computation graph to enable understandable natural language. Now, they refer to figure 2b here, and figure 2a shows where our benchmark positions among existing benchmarks, demonstrating the effectiveness of GSM-Infinite for long context reasoning evaluations. They conduct a comprehensive evaluation of 17 SOTA LLMs on zero noise problems and 10 LLMs on various noise injected tasks. We inclusively covered a wide range of models, including both popular closed source and open source, conventional and hybrid architectures, varying size, reasoning, and non-reasoning. In zero noise setting, recent reasoning optimized LLMs demonstrate substantial improvements. R1 achieves an average AUC 4 times higher than previous SOTA. However, in noise injected scenarios, LLM exhibit varying degrees of degradation. So the observations are LLMs follow a strikingly consistent sigmoid or exponential decay as problem difficulty increases. With noise, performance degradation intensifies as context length increases within the same difficulty level, while longer context brings sharper degradation. Okay. Then thinking patterns models consistently perform better on forward thinking tasks than on backward. So is backward just having like some kind of backtracking. I'm not sure what is backward thinking, and repeated sampling. So, repeated sampling on this infinite GSM-Infinite reveals a clear pattern. Performance improves linearly with increase in finished steps, but at exponentially growing computational cost, underscoring inefficiencies. I wonder if the exponential growth. So, what do you mean by exponential growth? Is that uh, the cost? Do you think of it in terms of the number of tokens used and then make the case for okay, not that is not exponential. Attention for that. Sorry. Ignore. I was saying right. So GSM Infinite is somewhere in this regime where you have context length going big and bigger, and reasoning complexity also going bigger and bigger, but not as big as frontier math. Um, Wait, position existing benchmarks across the reasoning complexity versus context length plot. Reasoning datasets are usually of very short context. Existing long context benchmarks are usually low in reasoning complexity. So our task can cover any context length that the user so chooses and can generate infinite reasoning complexity. However, for high reasoning complexity, our tasks need to use a longer context. Our task is shown in red. Okay. A simplified example of dataset building, we generate an interconnected computation graph and then we, based on the graph, attach real world context to it to formulate the problem statements. Okay, so you have adult lion at J Zoo, you have adult monkey at J Zoo, you have average newborn children per adult lion, you have average number of newborn children per adult monkey. You can divide total newborn average children at uh, Jefferson Zoo. Okay. So you have number of these. I don't really know how did they map to operations. Let me see. So assume any animals not mentioned doesn't exist. Adult monkey at Jefferson Zoo equals 2. Number of adult lion at Jefferson Zoo equals 4. Average newborn this is equals so it's mapped somehow. So average newborn children per adult lion equals 3 plus this. Average newborn children per adult monkey at this equals sum of average newborn children per adult lion and adult monkey. What is the total number? So you have to first calculate average number of children per adult lion, which is 7. Then you have to get average newborn children per adult monkey, which is 7 plus 9. And then total newborn animal are 2 into 9 plus 1 into 7, which is 46. Makes sense. And then this is the Cohen 2.572B instruct score across the 0 context 8K, 16K, and 32K. So you can see that as the number of reasoning steps increases, the accuracy also degrades, and as the context window increases, the accuracy also decreases. Alright. So related work and problem statement. Despite the wide popularity of existing long context benchmarks, this section reveals an average of the three key limitations: low complexity, detectable noise, and low resources or limited quantity of test examples. Uh, yeah. So the three key limitations make it extremely challenging to measure long context LLMs progress towards advanced intellectual agents using existing benchmarks. For low complexity, a significant portion of long context evaluation datasets, including ruler, long bench, and long bench, V2, and loft, primarily assess retrieval and summarization. As shown in Figure 3, our experiments demonstrate that RAG system achieve comparable results with Llama this across datasets. Notably, RAG outperforms LLMs in retrieval-focused tasks like these and performs comparably in text summarization, as well as structured reasoning problems such as variable tracking and code completion. So RAG is a strong benchmark. Like then detectable noise. Many long context benchmarks artificially extend short context tasks by injecting extraneous text that does not contribute to solving the problem, allowing retrieval-based models to filter out noise effectively. I don't know if this is as true as they're making it sound. Like This is the premise that your retrieval models need to be good for them to be able to filter out noise, and I don't think that is the case yet. I mean, they are good, but maybe not. They're not maybe perfect at it, which makes this valuable as well. In rulers variable tracing tasks with 8192 context, Llama 3.1 achieves 100%, while one pass RAG and interactive RAG get 82 and 98%, and despite only using a 2048 token retrieval budget. Detailed breakdown figure 5a reveals that, okay, maybe I was wrong. At least this benchmark seems to be saturated. Detailed breakdown in figure 5a reveals that retrievals consistently identify and prioritize relevant information while disregarding injected. These findings indicate that existing long benchmarks do not adequately justify the need for expensive long context LLMs, as RAG systems can effectively mitigate the impact of noise and achieve similarly low performance. RAG performance on a proposed long context benchmark. A studies the behavior on the first 100 chunks of a random problem in VT from ruler. The chunks are need to be retrieved to solve the problem and labeled as coral while the noise is in play. Uh, the chunks have retrieval scores range from large, semantically far, to small, semantically close. Retrievers locate the essential chunks with high precision, classifying all necessary chunks with the right side of the spectrum, search in the 100th percentile. For A, B contrasts VT with their long context benchmark, where they show that retriever cannot locate precisely which chunk to retrieve. C and D display the performance of two RAG systems on our benchmark. So the RAG systems have like additional accuracy as the problem become larger. Now, low resource, many high quality reasoning tasks heavily rely on human annotations and have test examples in limited quantity. Here they use GSM-8K as example shown in figure 4a. It is infeasible to extract substantive examples with exact opt at 8 for precise LM evaluation due to limited number of available cases. With even fewer satisfying operations greater than equal to it, the scarcity makes meaningful evaluation impractical. Also, Daphne bench, a high quality long context coordinate benchmark, only contains 782 verified and redeemed examples. Oh, this is interesting. I did not know about disability having very limited examples with long reasoning needed essentially. So the problem statement is how can we develop a benchmark that contains sufficient problems at every fine-grained level of reasoning difficulty, from easy retrieval tasks to infinitely hard challenges, by providing infinitely customizable context length with high information density. I don't really refer to figure 6 yet or even figure 4. So, I'll get all right, so computational graphs. In this section, we detail the construction of computational graphs, the key concept that enable GSM-Infinite generation of infinite quantities of arbitrary context length and reasoning complexity. Specifically, we explain in detail the potential mapping between reasoning problems and computational graphs. And in section 3.2, they propose to generate indistinguishable noise by strategically extending the computational graph. A graph construction to build reasoning problems. After carefully studying GSM-8K problems, we draw the following crucial observation, which allows us to map a randomly generated computational graph to grade school level math reasoning problems that cover all possible operations and relationship types. So mapping explicit ops to computational graph. For each operation is either a plus, minus, multiply, divide. Consider the following examples when operations are presented explicitly. So X cost twice as much as tomatoes, while tomatoes cost $1 each. These statements mention operations plus more times a check and can be easily be abstracted out as a computational graph with variables. So dollar per egg and dollar per tomato as nodes. The two edges one point from dollar per tomato to dollar per egg, while the other point from a constant 2 to dollar per tomato. Another similar example is shown in figure 6a, where randomly generating therefore randomly generating a computational graph with different topology of edge connection will lead to a new reasoning problem or once the natural language contexts are attached to the nodes of the graph. Okay, so you have lions in the zoo, dogs in the park, pigs in the park. So you have number of lions in the zoo, which is equal to and then the number of dogs is 5 plus number of thing, and then pigs in the park is sum of number of lions and number of dogs. Here you have number of pigs, number of dogs in the park is same as number of pigs in the park, and total animals is this. Okay. Now generating implicit plus using computational graphs. Now, on the other hand, the operations can also be presented implicitly hidden in natural language hierarchies. So things like Mary earns $20 in the morning while she earns $25 in the afternoon. How much total she earned that day? Although the problem doesn't explicitly mention addition, the solution has to do the sum. The reasoning in that natural language The reason is that natural language assumes a working day consists of morning and afternoon. So this is the implicit part. Similarly, all four operations can be hidden in natural language hierarchies. Inspired by this work, they adopt its construct of abstract parameters and instance parameters to construct computational graphs that facilitate the generation of problem statements containing the hidden operations. Essentially, the new added constructs can be thought of as adding the total money as a new node to the computational graph, which has two edges, morning and afternoon money. But when generating the problem, they omit the description of two edges pointing to the total node, total money on Friday. Okay. So they illustrate this in figure 6b. Following this work, we construct the specific instance parameters to the abstract parameters using red edges. To reiterate, these edges are omitted and then let's have to use common sense. Gotcha. So, this was it. Uh, I already read this. Given 1, 2 equals 1, what is 3? Breaks down the essence of implicit operation and the abstract parameter constructions here. An assumption provided in system prompt is to assume that animals not mentioned don't exist. Essentially, the problem in natural language omits the two red arrows in the computation graph. Okay, so you need you don't know explicitly that the total animals in the park is the sum of. Well, you're not asking for the sum of number of pigs and number of dogs, and you've just told it, you asked it to find the total number of animals in the park, and told it that there's only these. Don't assume, but you can assume that there are no other animals apart from the ones mentioned. Oh, this is interesting. Yeah. Okay. So this is implicit addition. Now implicit multiplication. Every variable in the above mentioned problem with the implicit adds in operation are two entity variables. The morning money containing two entities, morning and money, where money is an attribute of morning. Similarly, with afternoon money. In fact, out of all examples we manually annotated, the minimum number of entries in the variable name is two. However, if every variable in the problem are two entity only are two entities, sorry. However, if every variable in the problem are two entity variables, only maybe this is broken. There should be something else here, but they only generate implicit operations of plus and minus, but not multiply and divide. For a problem to contain implicit operations of multiplication, problems must contain variables with more than two entities. For example, Mary works 8 hours on Friday. Her hourly rate on Friday is $10. How much she will earn on Friday in total? So the variables are money per hour, where money uh, contains money, hour, and Friday, three entities where money is an attribute of hour, hour is an attribute of Friday. We further contrast our scenario in figure 6C and D. We see that if every variable is true entity or animal in location, generating multiplication isn't straightforward. But once they add a third entity or an attribute, generation of multiplication becomes natural. This is quite interesting. Let's go back to the figure. C provides an example problem where all variables are appeared are two entity variables where only implicit addition and subtraction can be generated. So you have number of lions in the zoo, number of monkeys in the zoo, total animals in the zoo is the sum. Given one or two, what is the total number of animals? Total animals is lions plus monkeys. So reverse is just if you want to find monkeys in the zoo, given one and three. Now, if you want a three entity thing, so you have number of lions in the zoo. We have number of average newborn children per lion in zoo. So what is the total number of newborn animal children? That is lions in zoo times average number of children per adult lion. And if you want to find average number of children per adult lion, you can do total number of newborn children divided by number of lions. Makes sense. D contrasts C and shows an example that with additional three entity variables, you can get both implicit multiplication and division. And finally, scaling up reasoning complexity and maintaining control with computational graph. A computational graph generator employs the abstract parameter construct to generate implicit operations in three entity variables to represent multiplication. During the generation process of a problem, specifically a query node is first sampled from the graph. The corresponding topological sort list extending with the query ensures the shortest solution path, serving as a measure of problem's reasoning complexity. This approach enables the generation of a vast number of synthetic graphs. Furthermore, adjusting the number of variables provides a coarse control over complexity, which is refined through precise filtering to produce well-defined subsets of graphs that meet specific operation constraints. Yeah, this is quite interesting. So I like how they've broken it up. I just wonder uh, why not scale up to like four entity descriptions and so on. But yeah. Now noise construction using computational graphs. Right at topology, we can observe that we can view noise as extending the computational graph to incorporate fake and unnecessary parameters and operators. However, two critical questions emerge. First, how to extend the computational graph without contaminating the original graph solution and contamination. We found that edges have to point to outwards from the node in the original graph to the newly added noise nodes, essentially preventing the noise nodes from contributing to the core graph. We found that edges have to point outward from the nodes. Okay, because if they point inwards, then the nodes will have some impact on the essential nodes. Second, how to maximize the chance that track cannot retrieve the essential graph. It turns out interconnected nodes between newly added noise nodes won't contribute help deterring rack's retrieval. They found a simple trick works well, ensuring that majority of added edges connect core nodes and the noise nodes contribute to semantically closed noise. And this is what they call spider topology, as in figure 6c. What is 6c? I didn't get this part. We find out a simple trick works well, ensuring that the majority of the added edges connect core nodes and the noise nodes, which this has broken English here. Ensuring that the majority of the connected of the added edges connect core nodes and the noise nodes, which contribute to a semantically closed noise. Okay. I don't fully understand this, but I'm willing to take a leap of faith. We evaluate the results using two axes in figure 2. The results are shown in figure 5C and D. Llama this achieved drastically stronger performance than the two rack systems on two entity and three entity problems. They also carried out the same study before on the dataset setting 2 in figure 5B. They found that the rack retriever now completely cannot distinguish which essential chunks uh, from noise chunks, showing a clear contrast with wiki tasks. Okay. Yeah. Now, GSM-Infinite. So in this section, we present techniques that enable the synthetic dataset to be diverse and understandable and enable the evaluation to be free from non-reasoning factors. Then we present synthetic problem generators capable of generating grade school math questions with arbitrary reasoning difficulty and context length. This is called GSM-Infinite. Now, first, how to generate implicit subtract and divide. Firstly, we review why the abstract instance can only generate add and multiply, not subtract and divide. The key limitation of abstract parameters and parameter design is that it only can generate solutions with forward and constructive ordering. Okay, shown in figure 6a and b, the design dictates that the specific and detailed variable should be defined before a more abstract. For example, the number of lions and number of monkeys have to be defined for total animals. The forward ordering leads to inability to generate implicit negation and division for two and three entity problems that require the more abstract variables to be defined before a more specific variable. Makes sense. So this is figure 6a. Okay, yeah, seen this. To generate all four kinds of implicit operations, we introduce a reverse mode to generate the computational graph. Essentially, the graph construction still continues as before, starting with specific detailed variables and growing to incorporate more abstract variables. When it completes and we know all the values of nodes in the graph, we then randomly mask out specific initial low-level variables and force the solution to traverse in the reverse direction as in forward ordering. We present the illustration in figure 6a and b for 2 and 3 entity. However, for 3 entity problems, it can result in quadratic equations leading to multiple solutions. They develop some techniques that effectively reduce the probability, and details are in appendix. I'll go over that. I guess the reverse thing are they said look at figure 6 and 6b for this. However, uh, wait, my alarm just yeah. Mm-hmm. I think I get it. I guess this what I tried to talk. Now, how to ensure LLM understandable problem generation. Mapping computation graph to natural language is critical, and to automate this process, they develop interoperable templates that enhance language diversity while maintaining clarity. Yep. First, certain syntactic forms, such as possessive constructions, are straightforward but can mislead LLM due to deviation from natural language. For example, South Zoo's penguin is restricted as penguin South Zoo, and South Zoo's adult penguin's average number of newborn children becomes average number of newborn children per adult penguin South Zoo. Through extended trial and error, variable names with different entity numbers are presented naturally in all prepared templates. I don't understand the problem in this. I mean, this example doesn't really show the problem to me. Maybe I'm missing something. Second, the number of constraints applied to the random graph generation process is as little as possible, forcing templates to enforce unit consistency across two and three entity variables. So the average number of animal children per penguin in South Zoo must share a unit with the number of penguin in South Zoo. Third, to ensure real world knowledge doesn't confuse evidence, they avoid specific real world things. Based on these constructs, they propose three different templates. That means real world template, children animal zoo, teacher school district, and award movie festival. An ablation study of these are in Appendix G. Okay. At each top, equal problems are constructed for forward and reverse settings. Now let's look at the benchmark details. With the synthetic generation detail in section 4, we then use them to generate problems to build a suite of reasoning tasks with increasing complexity. For the brevity of reference, we refer to the generated problems with the only explicit operation as easy, with two entity variables at maximum as medium, and with three entity as hard. Okay. Ideally, when evaluating an LLM, we want to evaluate all difficulty levels from the most basic to when it comes to fail to solve any problem. For the easy subset, it usually leads to large operation count for powerful LLMs. However, although complexity-wise not challenging, LLMs trained with internal chain of thought tend to generate very long arguments, saturating their API output generation limit. Uh, Thus, we observe a sudden decay in accuracy in large ops, not because of LLM's ability, but because of the above mentioned. Thus, we make a tweak. Instead of asking the LLM to find the value of One variable, we are selling to find all variables that have some value specified, effectively increasing the difficulty of the problem. Let me read this. Ideally, when evaluating, we want to evaluate all difficulty levels from the most basic to when it completely fails. For easy subset, it usually leads to large operation counts for powerful LLMs. However, although complexity is not challenging, LLMs tend an internal chain of thought tend to generate very long arguments. Thus, we observe a certain degree in accuracy in large operations, not because of the LLM's ability. Okay, makes sense now. For the modified EC subset, we keep the generated problems in the most basic form, symbolic assignment. A typical problem statement then becomes V1235 equals V this plus 1. Since the modified problem is not easier compared to medium and hard, they call it symbolic. For medium and hard, we use all three templates and mix the generated problems together to ensure diversity. They measure AUC, which is computing a Riemann sum over error performance and accuracy versus the number of questions. Number of operations from 2 to when its performance is lower than 5%. Okay, so as number of hops increases, the performance decreases. We prepare zero noise 8K, 16K, and 32K in benchmarks. The existing generation pipeline is capable of generating in greater than 60 million contexts, but the smallest 70B level models effectively failed in the 32K context already. While evaluating larger ones brings costs beyond our acceptance. Maybe this is a interesting way to put it. I mean, nothing wrong with it, but I've seen people usually say things like, "Oh, it becomes just too expensive," and not say beyond our acceptance. Let me look at the results. 18 selected models are evaluated GSM-Infinite, zero noise benchmarks under AUC, which is computed by taking the Riemann sum of accuracy versus outcome from 2 to when the model accuracy drops below 5%. We present detailed statistics of the first top number for the model to have an accuracy lower than 50%, 10%, and average accuracy of the first 30 of settings. Besides the highlight, I can't even read this. Reasoning models, linear attention hybrid models, and SSM hybrid models. Wait, am I colorblind or what? I can see the linear attention hybrid model highlighted, but I don't see any SSM hybrid. This is highlighted. Okay, this is maybe it's because my laptop is in the sun, but these two are very weird to look at. So you can see that first operation value at less than 50%, performance is at 100, less than 130 is greater than 130, and then average accuracy for number of less than number of 30 is 94%. What do these numbers mean is something I'm not. Oh, this is the EC. 10 selected models are evaluated based on infinite long context benchmarks using average AUC of symbolic, medium, and hard. They evaluate on different contexts, but although our pipeline is capable of generating longer, smaller models effectively fail at like 32K context length. And right, evaluation. Section 5.1 presents a complete comparison of LLMs on both zero noise and long context tasks. Beside the main leaderboard, we share further interesting findings. 3.2 sigmoid fade, 3.5.3 LLMs do better on forward and reverse. 5.4 LLM performance decay over long context. 5.5 G7-Infinite expression increase in inference compute yields ACGs. Okay, so leaderboard. They evaluated 18. We've already looked at these tables. From table one, you can see that score separates them into clear groups. Reasoning models are significantly ahead of non-reasoning. On the other hand, models with hybrid architecture aren't performing strong on the zero noise pure reasoning benchmark. Minimax and Jamba both severely underperform compared to 70B models. Also, similar things can be discussed when comparing 70B and 7B models. In table 2, we see that models show a very different decay pattern. Gemini 1.5 is significantly ahead of the rest of the models. Reasoning models evaluation remains too costly or slow for current long context leaderboard participation. Later on, we examine the behavior of elements on GSM-Infinite and summarize four interesting findings. Okay, so LM performance degradation can be modeled as sigmoid. Construction of GSM-Infinite enables precise measurement of performance over fine-grained difficulty. For each subtask, they observe a clear trend. LLM accuracy declines as the number of required operation increases. Surprisingly, most models exhibit sigmoid-like performance trend, as shown in 10 for forward problems. See section 4.1 for definitions. And what is definition of? I think they mean the definition of forward and reverse problems. Under the medium subtask, LLM performance aligns remarkably with the sigmoid or fit. This is a very good fit. The pattern is intuitive at low operation counts. Accuracy remains near one. As complexity increases, it first decreases gradually, then drops sharply to zero, where LM effectively failed to capture the problem. The score eventually stabilizes near zero. Interestingly, while LMs vary in overall capability, they follow the same trend. Where is figure 10? Oh, yeah, this looks remarkably like a signal. And so you have one which does better until a much longer window. Then we have Quen and a smaller Quen. Okay, sorry, I need to zoom out. Uh, so BNC is something they will discuss in a bit. The generator of GSM-Infinite can generate both forward and reverse problem, which can be compared separately. For most settings, perform reverse and reverse problems than forward problems using shown in figure 10b using machine large. For the medium, only Jamba large out of the total 18 units evaluated does for reverse better than forward. For the hard subtask, 5 out of 18 models have large reverse problem AUC. DeepSeek, Gemini, Cohen 7b, 4 million Jamba. The difference is 154. A detailed breakdown is listed in Appendix F. Besides LM performance and reverse volume can also be modeled by sigmoid mapping and extra plots. So forward only is better than reverse only for mission large. Okay, and then CMB is, I guess, discussed in the next plot. We evaluate a performance across increasing context when they observe a consistent decline as in context window increases. They present all results in for 10 models across three subtasks in Appendix H. The construct and evaluation study on three noise types GSM-Infinite, LM generated and random. For LM generated, the prompt 402 create field documented style commentary on random problems, occasionally introducing nonsensical variable mentions. For random noise, they follow this paper using generic state on the sky is blue, the TV screen. They evaluate this and the RAG system under all three noise types. Interestingly, RAG outperforms long context on LLM generating random noise, effectively filtering irrelevant context. However, it fails to distinguish for GSM-Infinite, which is nice. Yeah. Now, limitation of repeated sampling. The construction of GSM-Infinite allows us to study techniques for infinite sampling. Specifically, they study repeated sampling and its effectiveness under different reasoning complexity. They study both Quen 7b and Llama 8b with the best of n settings similar to Brown et al. Interestingly, they find that repeated sampling seems to boost performance the most for smaller operation count, and the benefit of repeated sampling diminishes gradually for larger operation count subsets. When 7b instruct behavior is plotted in figure 9a with repeated trial settings. Where is figure 9a? Okay. As you increase the number of trials, the accuracy does go down. And this is with different kinds of noise. As you increase the operations, the accuracy goes down. And even with RAG in different settings, GSM-Infinite is harder for RAG. Okay. Surprisingly, suppose we calculate the ASU score under every curve corresponding to each number of repeated trial settings. In that case, we find that increment in AUC score from two consecutive settings is low. If we plot AUC score versus the number of repeated trial settings and take the log scale of the repeated trial n, the graph is linear. R squared is less than 0.99. Therefore, GSM Infinite helps reveal the repeated sampling leads to linear AUC improvement, which is why they have like a linear. Since this is a log scale, it is a log linear plot. Uh, which is why you have like a linear trend versus on an exponential variable. So it's a yeah bad relationship. Effectively, you need exponentially more compute to get linear performance jumps. Conclusion: long context LLMs have the potential to tackle complex information and benchmarks and yada yada. Yada. Yeah, really cool work. Let me quickly go through the appendix. So long context LLMs, you need tree attention, wing attention, flash attention, and so on. To do well, you have architectural strategies as well. You have all of these benchmarks. Fair. The limitations is not good for challenging evaluation. Synthesized data, uh, yeah, synthetic tasks are nice. Now the limitations. So you don't have more complex operators, which they are planning to incorporate in the next version. To generate complex problems with high reasoning capability, the generator needs to generate problems that are much longer than hard mathematical benchmarks, despite our limitless quantity. Another key limitation is the lack of diversity in natural language, and you can basically do that without. You basically cannot do that effectively without having an LLM in the loop kind of setup. Uh, we do notice that when processing through noise, the LLM sometimes are confused by irregular noise. This is the repeated sampling generate 256 samples at temperature 1, fix it for reproducibility, and then they get to compute the number of correct things and accuracy for n samples. And now some small implementation tips about quadratic or higher order equation. The quadratic equation gives rise to particular situation. For example, reverse mod questions. One easy way is to assign the variable asks as x, perform symbolic operations carrying x and go through the entire computation graph to close the circle. Using that equation would easily solve for x. However, sometimes the query variable is too deep and it might assign both variables y and z, which are later multiplied. Then two linear expressions are multiplied to get quadratic operations. And as an operation becomes larger, it can be more severe than quadratic. To alleviate the situation, we found the following technique to be helpful, empirically helpful. When generating the problem state, we first look at the variable that has the largest number of entities in the variable name and make sure that one of the end of the topology sortlist during the forward and make sure that that one is one of the end of the topology sortlist. And then when switching to reverse mode, we locate the last possible initialized variable so as close to the end of the sort list as possible and assign this variable as a query, effectively reducing the chance of its dependents multiplying each other. Okay. The method can reduce the chance of quadratic or higher order equations happening. However, if we still encounter the case even when lower pressure is placed, they discard it. Okay, makes sense. Yeah, overall, really cool and interesting paper. I had fun reading it. I think there's still a lot of room to improve the writing. I think they're also constructing a second version of the paper, which is also nice. So yeah, overall, really fun. And thanks for tuning in. See you guys again next time.